I will talk to you a little bit about what we call RF compatibility testing and how we do this at the European Space Agency. The European Space Agency is responsible for the European Space Tracking Network, which is a network of ground stations used to communicate with satellites. It's operated 24/7 from the European Space Operations Center, also called ESOC. Of course, because we are a space agency, we need to have acronyms and abbreviations to keep the barrier of entry as high as possible. Which is also located here in Darmstadt. Today there are more than 20 different missions supported. They range from near-Earth missions in what we call low Earth orbit. This is a few hundred kilometers up to highly elliptical orbit, which has the lowest height of a few hundred kilometers to a few thousand kilometers. And we have a few missions in the Lagrange points, which are stable regions of the Earth-Sun system. Some are about 1.5 million kilometers away from Earth. And then we have another category of missions which we call deep space missions, which are typically around other planets like Mars, Mercury, Jupiter, and Venus. We have, I will show later that we have many different ground stations that are communicating with each of these type of missions. What makes it a bit special is that each mission is generally very unique in terms of its design and its objective, its instruments, and you can think of it as a custom-made machine that there exist no copies of it. Of course, some missions have multiple spacecrafts, like Galileo, which have now almost 30 spacecrafts. Some of them are also very expensive, with budgets of more than 1 billion euros, like JUICE, which I'm showing here, which is currently in transit on its way to Jupiter. We also have Bepi Colombo, which is on its way to Mercury, and we have a mission called Envision, which is in the planning, which will go to Venus. Here you see a map of the European Space Tracking Network, or ESTRACK for short. The blue circles are the ones that are part of the ESTRACK core network, and then we are also collaborating with the NASA Deep Space Network and a few commercial providers and other space agencies. To communicate with our deep space missions, we have a ground station here in Argentina, one in Spain, and one in Australia. For communicating with polar orbiting satellites, it makes more sense to have it closer to one of the poles, so we have located one in Kiruna, which is in the north of Sweden. As I mentioned, because these are pretty much unique, so how do you know that a newly launched satellite will be able to communicate with the ground station? Do you want to wait until it's launched and hope for the best? Or can we do something better? Testing when it's in orbit, I would say, is quite risky. Failure is not an option, and so on. Or do we simply move the ground station to where we build the new spacecraft? It's a bit impractical because it's not always being built in the same place, and the ground station is quite big. We can also send the whole spacecraft to the ground station, but because we want to locate the ground station in a RFI suitable environment, it's very difficult to get especially a maybe 1 billion euro machine to this location. Unless, by chance, the spacecraft needs to go there anyway, which is the case for our ground station in French Guiana, in Kourou, which is also where we launch the spacecraft from, on the Ariane 5, 6 and the Vega launchers. But of course not all missions are launched from there. Recently we have also launched a few using the Falcon 9 from SpaceX. So what we have since many years now have had here in Darmstadt is what we call the ground segment reference facility, which contains every subsystem from the ground station, representative version of it. And instead of bringing the whole spacecraft to ESOC, we take out the important parts, most importantly the transponder, which is the RF system, along with the onboard computer, which is used for generating data and receiving commands. And we pack it together in this rack, which we call a suitcase, because it's so nice and small and portable, relatively at least. After we have done sometimes several weeks of testing, sometimes even months of testing, we issue a statement of compatibility, which is a requirement before the launch. If we find any problems, either we have to find workarounds or we have to go back to the drawing board, but at least we are aware of it and we don't get any surprises when it really matters. The list of tests we perform is quite long, so it can take a very long time depending on how complex the mission is. The CCSTS actually defines a list of a minimum set of tests to be performed. So there are even more than this. This includes things like frequency stability, measuring the spectrum, measuring frame and or bit error rate, measuring the ability to command, so both from space to Earth and from Earth to space direction, measuring the ranging using the same signal we use to communicate, measuring the Doppler, and also the stability of the ground station. Here are some figures just so you have some idea. The signal levels arriving to the spacecraft can be in the order of minus 155 dBm up to minus 50 dBm, so it's quite some dynamic range. The signal to noise density we have on the other direction can be as low as 20 dBHz up to more than 100 dBHz, depending on how far away or how close it is to Earth. So also some dynamic range there. When we're talking about data rates, we have sometimes as low as only a few tens of bits per second, or symbols per second in this case, up to now soon 500 megasymbols per second. Here are some example results that we might find. We measure the phase noise, we measure the spectral purity, and we measure the frame error rate and compare it to the theoretical or simulated results. All of this goes then back to the operator link budget, not only to have the theory, but to have really the performance of the system as well, to take this into account. This is just a very basic setup. We have the ground station modem connected to a frequency converter to get it to the frequency we want. We have a ground to space channel, which in this case is just some attenuators and diodes to precisely control the level. This goes then to the transponder, which is connected to the onboard computer. On the downlink channel, we have also a noise source to simulate the signal to noise density ratio. Going to a frequency converter again to get it from the RF frequency to the IF, which is what the modem supports. What we have recently realized to reduce the amount of risk when we actually bring everything together is that we can do a bit of preparation. If we can only record the signal transmitted from each part, we can actually send it to the other side, which might be in another part of Europe, or even sending it from Europe to the US in case we are supporting NASA missions. And this is done via OneDrive or Dropbox or even email if you have a small file. But of course, as you can see from this, the files are either very large because they have such a high bandwidth, or if we need to measure the frame error rate down to 10 to the minus 8, and we are operating with 10 symbols per second, it will go over a very long time. So this is only something we have recently started with for the Hera mission, which will go to investigate the results of the NASA DART mission. We recorded some samples from the real spacecraft in OHB, which is building the satellite, and sent them to ESOC. For NASA's Roman Space Telescope, some samples were recorded at Goddard and sent to ESOC so that we could do a first test of our new implementation of the LDPC 7.8 decoder. And in both cases, they were played back to our ESTRACK specialized receiver using GNU Radio and the USRP N320. That's it for me. Thank you.